Hello and good evening. Welcome to the inaugural lecture for Professor Ashiq Anjum. It's my great delight to welcome you to this College of Science and Engineering event that's part of our Centenary this year. In a moment, I'm going to hand over to Professor Liu, but I just wanted to welcome you all to colleagues, friends and family from the UK and around the world to this lecture. Today, Professor Anjum is going to talk to us about edge intelligence, the next stop in the evolution of distributed AI. And as all inaugural lecturers are, this will be a food for thought and a look into the future of the subject. So without further ado, I will hand over to Professor Liu to introduce the lecture in his role as head of school. Thank you.
Good evening. I'm Professor Liu, head of school for computing and mathematical sciences. First of all, I would like to briefly introduce my colleague, Professor Ashiq Anjum, to you. Professor Ashiq Anjum is a professor of distributed systems at the University of Leicester. His research areas include data-intensive distributed systems, distributed machine learning models, and a high-performance analytic platform for streaming data processing. Professor Anjum had participated in a number of the large projects, including EU-funded projects on medical data analysis and distributed clinical intelligence. He has been investigating large-scale distributed systems and an analytic platform for LHC data in collaborating with CERN at Geneva, Switzerland for the last 15 years. He has also been working with aerospace, rail, and automobile companies to investigate how infrastructures and services can benefit from real-time analytics of the Internet of Things data streams for accuracy, reliability, safety, and capacity. He's working closely with a leading virtual reality provider for developing AI-driven digital twins and enable real-time visualizations of the data models in virtual reality environments. So I'm not also going to take more time. Now I would like to invite Professor Anjum to deliver the lectures entitled Edge Intelligence, the next stop in the evolution of the distributed AI. Thank you.
Thank you very much, Professor Sarah Davies and Professor Liu for your nice introductions. And I am grateful to all of the colleagues who have joined us in this talk. For the next 1 hour, I would be explaining edge intelligence, what is the next step in the evolution of distributed intelligence. I would be explaining my own projects as well as examples to just give you a brief that what's the past, what's the present, and what's the future of distributed intelligence, and how this is going to transform the next generation research and development. I would be requesting my colleagues here to if I could share the slides, please. Thank you very much indeed. So this is a brief outline of my talk. So I would be starting by explaining the reasons why we need distributed AI. I would give a few examples of large amounts of data that need distributed AI models. I will then briefly touch upon some candidate approaches in distributed AI, and then I would continue to explain the history and models for centralized, deep, as well as edge-enhanced AI models. During the discussions, I will highlight key projects and examples from my own research, and I would be presenting some key findings as we move along into the presentation. So I will then set the scenes for future, where I would highlight how edge intelligence is going to transform how we process data, how we build models, and how we produce next generation applications. So that's a brief outline of the talk today. I would be starting with this particular screenshot from The Economist. And they suggest that the world's most valuable resource is no longer oil, but the data. So, and this would transform how the next generation economy, next generation business, and next generation technology is going to shape. So, so especially the industrial, fourth generation industrial revolution would recognize or already recognizing data as a raw material. And this would be a source of competition by leading organizations, because they would be able to, or they would have the capacity, or they would be building models and putting resources to produce research that is leading edge, and then they could monetize or they could exploit the data in ways that has not been seen before. So obviously, the most valuable resource is data. Now, how much data we have and what are the sources of the data that are available here? So, I took this particular kind of numbers from a local newspapers, and that suggests that there are around 6 million cameras in UK. And if we map the number of cameras to number of people, essentially there is one surveillance camera for every 10 people in Britain. And they are generating exabytes of data. Now, we also see in parallel that anything that could produce data or that could consume data or that could sense is known as Internet of Things. And Internet of Things is where the digital world meets the physical world. So now in that particular sense, our cameras are also IoT devices, and they are generating exabytes of data actually, so per year. So for example, in London alone, there are 1 million plus cameras, and they generate almost petabytes of data every month. Now, there is no infrastructure or there is no hardware that money can buy to simply store this data, let alone process it. So this is a big challenge that we need to think of new models and new approaches to not only acquire data, transfer this data, store this data, and process this data. So, so there is another example in a similar word. For example, particularly, for example, in aerospace. So aerospace and other kind of high and applications are becoming increasingly sensor enabled. They are becoming instrumented. They generate huge volumes of data, and obviously at an enormous kind of speed. So for example, in Rolls-Royce engines, there are 1 billion lines of codes, and each engine generates 10 terabytes every 30 minutes. So it means that if a flight starts from London Heathrow and goes to John F. Kennedy, they would be generating 640 terabytes of data because there are 4 engines. And this is just one plane. Now just multiply it by thousands of flights. And just we also have to look into the factors that on each plane there are on each wing on the plane there are 15,000 sensors. So if we simply multiply the numbers and simply kind of translate this into data, so it means that there is so much data that no amount of hardware would be able to store it, let alone process it. So it means that we are drowning in data day by day, and our ability to process this data is diminishing because we are generating more data actually. So now this is another kind of dimension of that. So as we are generating more data, it means that the percentage of available data an organization or enterprise can analyze is decreasing proportionally, because it means that we are generating more noise or we are generating more data, but the valuable information that we could extract from that data is diminishing. So it means that the ratio between signal to noise is changing. So in other words, that as enterprises, we are getting more naive or less kind of informed about our business over time. Actually, we do not know what kind of value or what kind of information or intelligence we could have actually. So from our data actually. So we know there may be a value in this data. So we need to sift through the noise to find value. But obviously, this would need a lot of infrastructure, a lot of resources, and we need to do it in real time because more and more data is arriving all the time actually. So how can we monetize simple unknown relationships, unknown essentially a kind of a contextual information, unknowns, a kind of a noise actually. So because at the end of the day, anything we cannot process is a noise. So how can we convert that noise into a kind of actionable intelligence and information that organization could use? That's becoming a big challenge. So this is the next kind of bit of that. So it means that as the passage of time, we are generating more data actually. So, for example, there is a rough estimate that we would be generating around 6,000 exabytes of data. In the next a few years. Now, so today we could only process around 12% of that data. Just 12%. It means that 88% of the data that is available to us, we cannot process. That's a huge amount. It means that we are only aware of the fraction of the potential that we could extract or exploit from our data actually. So it means that we are becoming to some extent less informed and a kind of less knowledgeable about our own kind of business that where we are operating or we are working actually. So now, having said that, so this is ongoing kind of research and development question. So that what can we do to basically process that data? Historically, people have been proposing AI models. And just to cope or to counter this scalability issues, people coined up the term distributed AI. And the first thing was that how can we parallelize that? How can we parallelize the data? How can we break the data into chunks and can store on different machines? And then we build machine learning models on top of that so that the whole model runs at a lot of different places. So it means that the same model is running on different chunks of data at different places. So a model is replicated across the machines, and obviously they are distributed. So this, by the way, in the data parallelism, this is one of the possible approaches to process this data. It could be a distributed system, could be cloud, or it could be HPC, or it could be a kind of mixture of that. So, and the model is replicated across the distributed machines. Now, this model has been most prevalent model across the application landscape. And from late 90s, people have been using data parallelism based AI. So because it's easier to implement, it offers strong fault tolerance. Some of people may be aware of Hadoop and Spark and other kind of distributed data processing frameworks, or even grids, for example. So they implement data parallelism as well. Almost all clouds implement to some extent data parallelism as well, especially if the data is distributed as far as the storage is concerned, and the throughput is important consideration. Throughput is important because each algorithm run independently. They're not talking to each other. The data is distributed. So as a result, we could achieve high throughput from the distributed data. So this was just one of the aspects of data processing. Now, there was the second approach as well, where we say that we should not just distribute the data, rather the data may be as it is, rather we should do a model parallelism. So model parallelism is that that instead of running one models across the whole machines, and the same models have many copies, we know that the models are becoming large and complex. There is not enough space and enough capacity to host the complete models on individual machines, especially as smaller devices such as mobile phones and GPUs are being used more and more in the learning and in the inferencing process. So what we do is we break the model across machines and then join individual pieces to produce the output of the whole artificial intelligence model. So recently, with the prevalence of mobile phones and mobile devices, this is becoming a kind of quite a common model. So the reason is because it's good for scalability, as large models cannot fit onto small machines. It is less on a kind of requirement on memory because they could fit into a kind of resource constraint resources such as mobile phones. Um, so so um, so this is becoming the most prevalent kind of AI model as more and more people are exploiting different types of data and different types of models and different types of hardware resources actually. So this was the second kind of most important approach people have been using during the course of last few years or last decades actually. And the third the people have been using, it's a kind of model parallelism. It's known as a federated learning, and this is becoming a more and more kind of prevalent due to mobile phones and smart homes and smart cars, and as the devices or IoT devices are becoming mobile. So we are seeing more and more federated learning, and federated learning is essentially where a number of local models collaborate and cooperate to produce a global model. So this is very similar to model parallelism. So the good thing is that only final readings are exchanged between the local models, and there is no data exchange. When I say the local data it means that only the final readings exchange, no raw data is actually exchanged. Just I explained before, federated learning indeed implements model parallelism, this is essentially a collaborative training of a single global model by collaboration or cooperation of many local learning without exchanging or transporting data. And especially if the data is sensitive, if the data is high value, there are ethical and legal issues that we cannot transfer data, then federated learning is the best way forward actually for the learning process. So that was a quick overview of what of different distributed AI approaches are available over the course of last few years and how people have been using it. Now I would be starting the next phase where I would be explaining what are different applications or different projects over the last 20 years. And how they have been implementing AI, and then I would be breaking down the use and a kind of as well as the exploitation of AI into 4 waves actually. So this is the first wave, and probably most of you know that LHC, Large Hadron Collider, is one of the largest experiment in the world. It's in Geneva, Switzerland. And probably you know that CERN was the place where World Wide Web was invented in 1989. Interestingly, I spent almost 7 years there during my PhD. And so I know quite a bit of this, both in terms of software and hardware, because my PhD was exactly on this particular area. So, and there are hundreds of different organizations. They are working together to essentially a kind of process the data that LHC experiments producing. In terms of data productions, they are generating 15 to 20 petabytes of data every year. And just to process this data, we need at least 100,000 cores actually to process this data. And they are generating data in many gigabytes per second. And just the final bits of the data that need to be distributed is 1 gigabits per second actually. So it's more than essentially 1 gigabytes per second, and that's a huge kind of commitment in terms of data storage, in terms of network capacity, and in terms of the processing availability. So this was essentially the first wave of AI, what we say that how people were doing in 2000, early 2000, for example. So people were doing locality aware scheduling or locality aware analytics. Locality aware analytics is where we it's essentially data parallelism. Data parallelism is where we only break the data across different clusters. Then there are hundreds of clusters all around the world. Then we have our statistical algorithms that we run on individual clusters, and then the results are produced in individual clusters, and then they are sent back to the workflow who initiated that particular application actually. So this is very network intensive. This is data intensive, and this is a compute intensive process. And all these algorithms and applications run in parallel. By the way, data is replicated, and there are more than one copies of the data for resilience as well as for fault tolerance. And then different machines collaborate so that to basically avoid heterogeneity issues, avoid communication and collaboration issues, avoid resource management issues. So essentially, this is a cooperative scheduling that implements the lower level kind of infrastructures. On top of that, because we don't know what is the capacity on individual clusters, so this is more kind of a speculative scheduling. We know that the resource may be available there, so our algorithms should be sent there. Now, essentially, these are mostly statistical algorithms. At that moment, if we want to basically run something again, we would have to run the whole algorithm on the whole data again, because there is no kind of learning either saved or there is no evolution. So each bit of the algorithms runs in parallel. This is not there is not learning involved, because obviously this was more kind of computing statistical kind of values out of large of data and then putting together all the basically results to find a combined value, and there was no kind of deep down machine learning involved during this phase. So this was one of the projects that was using the first wave of AI, what we say, or the first wave of intelligence. On a similar time frame, we did a similar project, but for different types of data. And this was for neuroimaging community. So this was a European Commission project. So what they wanted to do was that they wanted to kind of process individual brains to see the impact of different kind of stages or the impact of different medicines on individual patients as far as the dementia or neurodegenerative diseases are concerned. So they wanted to basically improve the diagnostic and prognostic accuracy. They wanted to check the reliability as well. And essentially, during this process, we built a whole grid across Europe. And on top of that, we connected different hospitals and more precisely neuroimaging centers. And from the neuroimaging, they wanted to calculate different brain, essentially kind of parameters, for example, white matter or dark matters and that kind of things, to see that how a particular neurodegenerative disease, for example, dementia, is progressing over time, and what is the correct time and how early we could detect or basically a kind of prescribe medicines actually. So so this was particular the approach. This was again the first wave of AI. So that was not the this was very close to more the statistical algorithms. We were using a kind of multi-objective optimization. So here we have a large workflows, and what happens is that there are hundreds of steps in this particular workflow, and so these basically some of those steps they could be distributed. So a whole neuroimaging workflow can be having hundreds of steps, and those hundreds of steps could be executed on different sites. And then we map this particular workflow onto a multi-objective optimization algorithm. So each brain image takes around 18 hours to process and has 220 GB a kind of space size or total data size. So there are hundreds of thousands of imaging requires days to process. We planned that this should be executed if we don't run this particular kind of algorithm, then this may take days or even months to basically get the whole data processed. So what we did was we implemented this particular kind of approach, and we then used the underlying grid computing power grid was the quite prevalent distributed system infrastructures. So now we also looked into redundancies. We looked into workflow planning, that which bits of the workflow should be executed on which bits of the data and which bits of the hardware to basically increase efficiency and cut down the processing time. So we reduced the processing time from many hours, that was 18 hours per image per machine, to few minutes actually. And if we simply multiply by hundreds of thousands of different imaging or scans, I guess that was a huge kind of achievement, but still there was no learning involved. This was simply a kind of a very compute intensive process. This was not scalable. We were throwing hardware into that. So again, this was a first wave of analytics, and this was early 2000. Then around 2005, people started producing kind of neural networks, or this is the time when people started thinking around the deep learning. These were the early days of deep learning or structured neural networks actually. So and in this there were hierarchy of features. The people were putting together the features into layers, and each layer had the same structures, and they were stacking multiple stages of features to extract features of interest actually. And each layer manipulates the data locally, and then we put together all those local features into basically some kind of relationship or convolutions, and then basically we keep moving. And this is very iterative kind of process. And there was, and even up to this point, there is no basically kind of a fixed structure or fixed a kind of a mathematical model that how many layers should be there, or how many a kind of iterations we possibly can have to get the results. So it's mostly experience and by trial and error, and we can basically keep doing this step. Basically, we say stretching and squashing the data until all the data has been correctly classified. And again, this is a very centralized infrastructure. Everything works in one data center. It's very hard to distribute different pieces of the deep learning network onto different machines that are not within the same network. So due to some reason, this became very popular because this converted, or this translated previously handcrafted features into more machine readable features. So this was a kind of a big evolution, but it was still a central evolution. So for example, one of the projects that we did with local kind of companies and some law enforcement agencies was that we started processing the video streams that are coming from different cameras actually. So and we built a cloud data centers, and then we built a kind of Mahout-based analytics environment, and we built deep learning networks within the cloud actually. And that was a kind of quite parallelized environment because we were implementing Spark clusters, because we were extracting a lot of data that's coming from video streams actually. So, and because at that moment there was no 5G or similar like kind of network infrastructures, so we had to implement RL300 recorders so that if somehow our stream is lost, we should have a local copy. And then when this data is basically sent to clouds, we used our algorithms to basically kind of process that into individual objects, and then we implemented a dashboard, said that we could search individual features based on the object type or object size or object location or object history or time of the day or time of the year actually. So but this is again a very time consuming process. This takes simply I mean, as the data sizes grow and become large and large, it takes a lot of time to process that. So because there are a lot of stuffs in this pipeline that are very that's a very compute and time intensive, and this is not a real time process. If we want to track an object in real time, this would not give us. So now this was the analytics pipeline that we were using. So what we do is we have a number of camera streams or camera feeds coming from different cameras that are distributed. So and what we do is we detect individual targets and we localize them. So and then once those individual targets are detected and mapped, we then want to see that what is the inter association between those frames, because obviously one object may be a number of the streams that are coming from a particular camera or particular kind of sensors. And then once we have established inter association tracking, then what we do is we then map basically that what is the likelihood that the same objects may be available across number of different cameras actually. So this what we say is inter-association tracking actually. So once we have done that, so then essentially we link together into a trajectory, and what we say is that's the multi-camera motion association semantics actually, because we could then map this into a Google map or trajectory or into time-based a kind of a movement. And so essentially retrospectively we could track an object, we could map the locations where the object has been, and we could pinpoint precise locations. But the challenge is that is retrospective. That is more like a forensic analysis instead of a real-time analysis. And obviously this is one of the issues because the time is of concerns, time is of value actually. The second thing is that we need to store and bring all the data to a cloud. This is a very expensive process because you cannot store all the data if there are a million cameras, because they will be storing exabytes of data over the course of few years, and so the cost to store and process is simply enormous, and this is not sustainable and this is not scalable. So that was again basically the second wave of analytics, what we say. So, and this was the time around 2008 and 9 when we started thinking that, oh, by the way, there is a new wave coming because millions of new devices started emerging. There were more and more people basically coming on the internet. So, and we started seeing that from 10 to 20, actually, there were essentially billions of new devices added into the total basically device landscape. So for example, now we have more or less 50 billion devices. So the number of people growing and the number of devices growing, they did not have any kind of links, because obviously devices were growing at an enormous speed and they were generating so much data. So, and this was the time when people started thinking, by the way, we are into an IoT era. We are into era where these devices are not dumb and dull devices. Rather, they should be having a different role, and we should start using them a kind of more intelligently, actually. So yeah, so 2008 and 9 basically was very important time actually. So, and they also started thinking that the centralized approaches, they are becoming too impractical, because they're slow, they are expensive, and the amount of data that's being generated, that's petabyte of data each week, that cannot be stored. So no centralized approach can process this data within the centralized approaches actually. So that was the time when people started thinking into new set of approaches. So So, and these were some of the challenges of centralized intelligence. So as more and more nodes are added to the network, so latency becomes too high because obviously there's too much data. Transport cost to transfer that data from the device to the cloud becomes too much as well. And the resilience become impractical as well because some of the data is lost, some of the data is missed, there is no much consistency. So and yeah, so and due to different reasons, the people thinks that the current centralized infrastructures where all the data is transferred from edge devices or from the mobile devices or from the end users to the cloud needs a different thinking. And this was the time when people started thinking that centralized intelligence, centralized AI is becoming a bottleneck. So, and this should start thinking to basically evolve into a different kind of approach actually. So during the same time, people started coming up with different applications, for example, remote surgeries, virtual reality, real-time surveillance, autonomous cars, and as IoT were enabling a different set of applications, but underlying AI model was not there to support that. So, and this was the need, or this was the requirement that we should come up with a different model. So, and this is what we say is the third wave. Third wave led us to a new kind of paradigm, and we said that it's edge enhanced learning. So, and instead of centralized kind of data processing, we say the localized learning and inferencing. Algorithms become slimmer because obviously they need to fit into a kind of resource constrained devices. Data is processed on the edge. So training is still in this particular wave, training is still happening within the cloud, but inferencing was becoming more and more prevalent on the edge devices. So, so one thing that happened was that people were basically doing more and more data reduction on the edge. So some of the algorithms that were trained in the cloud, they were being shipped on the edge so that some of that intelligence could be used to cut down the data sizes. So there were two themes happening. So one was the data reduction, and the other was the more kind of agile and kind of slimmer algorithms that are finding its way into the end user communities. So we started thinking that why not we should use the same approach to basically process the video streams that we were processing before in a different way. So what we did was, so we basically started using the cameras that that originally were being used as a kind of data producing entities. Now all of a sudden we have started using a kind of the same infrastructure, a more kind of a data processing as well. So, and this was very, very important because all of a sudden 1 million cameras or 1 million nodes that were only producing data, now at the same time they could also process data as well. So all of a sudden our cloud has been extended from one place to basically onto million different nodes actually. So this was the third wave where we say we named it in transit analytics or in transit edge analytics, because not only the devices, rather the intermediary infrastructure that connects the cloud and the edge devices was also being exploited actually to produce more or less real-time analytics actually. So, so this was a huge kind of change in how we produce data and how we process it. So here the algorithms were still being trained, or the models were still being trained within the cloud, but they were finding increasingly its way into more inferencing or the data processing. Now, obviously, all those kind of applications that previously were exploiting centralized analytics, this could be LHC experiments or smart grids or smart cards or genomic machines or square kilometer array. So, and had the same data rates. Basically had a fantastic kind of a new framework that could exploit, or that could be exploited to make the existing centralized analytics into decentralized analytics for real time and low latency kind of analysis. So this was a big kind of things. So we did some experiments here, and we produced basically not only a kind of a whole architecture, rather we also got some statistics as well. So we said that it's not possible that that the current centralized training would be working as well. So what we did said we said that we should be breaking the deep learning pipeline and then distribute the individual stages into resources so that resources could be scaled up and down based on the data streaming rates actually. So what we do is we then basically train the model and then break the pieces into different stages, and each stage works on a different hardware depending on its edge resource, or it's in transit, or it's a cloudlet, or it's a cloud resource. And so we then run different kind of simulations, different kind of partitioning strategies to see that if we run this particular layer of a deep learning model on a particular resource, what is the performance we would be getting? What is the computational efficiency we would be getting? Now, there are two simple rules that if we process the data close to the sensors, we would be kind of decreasing latencies. And if we process data close to the clouds, obviously we'll be getting more compute power. So essentially, this is a kind of bio-objective process, so that if we need real time, then it means we need to send less data so that we and we could process most of the data on the source on the mobile devices or on the data capturing devices on the data sources. But the challenge is we don't have much resources, so we have to have a balance actually. So initial results suggested that we could cut down basically the processing time to 50%, and we could cut down the bandwidth to almost 99% by decomposing the models actually. And we proposed a T-block architecture that gives us both horizontal scalability and vertical scalability. And we said that this is one of the examples of a third wave. We implemented another application on top of that as well. So and this was a kind of data compression. We know that we may not be able to process all the data on the edge device. So what can we do is we can process some of the data on the cloud, sorry, on the edge, and then we could basically compress rest of the data in a way that any latent space or any kind of additional dimensions that are not required during the processing steps, we could simply cut down on the edge actually. So this compression basically would reduce the number of streams or the size of the streams, as well as the total data that is being sent to the clouds to basically many folds. So far we have been able to cut 99% data redundancy without losing performance. So what we have done is we have trained different kind of classifiers. We say this is a low quality of service, this is a high quality of service, this is medium quality of service. Then based on the data characteristics, we pick up the models. We have a quality of service tuning engines that would understand the data requirements, pick up the models, compress the data, and send it to the cloud where it would be reconstructed and analysis would be performed. So this way, we are not only cutting the data size, cutting down the data size, rather also we are removing the redundancy. And as a result, we are making more space available, not on the edge resource, but also on the cloud side as well. So this is basically becoming more and more kind of powerful, because data compression or data reduction is a quite old problem, but with the edge devices, this has got a new kind of life, and we have been using autoencoders to implement the coding process, and so this has been very successful. So we say this is essentially a kind of a data compression kind of process. So now another thing that we have been doing is that how can we basically do the data processing in more or less in real time actually. So that has been the process going on for quite some time. What we do is we say this is adversarial thresholding. So what we say is that we implement a number of different models, and each model could process one set of streams, and then we have a number of different models that could process different streams. With each streams, we could train individual models. Then we pick up the model that gives us the best results, and that model is instantiated, and that model then basically start processing the data. Now, during this process, we think that accuracy is decreasing. Another model is basically trained, and that model takes over and essentially would start basically processing. We say it's exploration versus exploitation. Exploration is that which is the best model. Exploitation is that how could we effectively use that. Now, different applications have been proposed, so I would be just presenting one or two applications here. For example, one of this is predictive maintenance. We have been doing a project with a company in Derbyshire. So what we have been doing, we have been using the same approach that I discussed previously to essentially offer a kind of a predictive maintenance model. So what can we do is we could use edge intelligence to combine failure models, criticality analysis, and effects to enable basically to enable a model that could offer essentially insights that when a particular machine or particular train or particular moving parts needs to be serviced or needs to be replaced. So this would give us a good understanding of asset conditions and timing of type of the maintenance intervention. So this is one example of edge intelligence and semi-bandit learning for the benefit of predictive maintenance that we have been using actually. So that was so far the third wave. It was that we train the model on the cloud and then we process that on the edge. But obviously things are changing. Time is changing. So now what if there are thousands of devices that are in the field and they're running, collaborating, they are basically interacting with each other. So simply training in the cloud and then instantiation on the edge is not going to suffice actually. So what we need to do is we need to basically put together the data, the people, and the devices into a model. And that is essentially, we say it's a consistent model, and that we say it's a digital twin actually. So what this should do is, so that if there is no individual device, there is no individual applications, rather it could be a whole factory or whole process put together to number of, it could be hundreds of thousands different devices, and to create a complete story. And this digital twin essentially is a physical phenomena that's mapping essentially the digital worlds and the physical worlds will be coming together. So so essentially this is what we say is the fourth wave actually. So essentially context is involved. Context is essentially that machines and processes should make localized decisions in their own operational environments, then collaborate with other kind of machines and entities, and collaboratively they should create a complete picture, or they should make the puzzles, and that puzzle should be a complete applications, a complete process. And previously it was the only information that was being basically sent to the cloud. Now the environment becomes intelligent because that is composed of hundreds of thousands of different sensors, and those sensors are cooperating with each other to make basically more kind of global or cooperative decisions. Now the two applications that are making use of this is a virtual reality and augmented reality. Now virtual reality is essentially it produces the model, and augmented reality is that consumes the model and then augments data on top of that, so the new data is arriving, the model is evolving over the course of the time as well. So we have been working with Rolls-Royce and Block Digital to basically work on this contextual edge intelligence, and we have been producing digital twins. So I would be explaining what and how we are doing in the next few slides. So, and other reasons, other thing that we need to do is, so even if we have a contextual intelligence, if we have to make it useful, if we have to make it practical, if we have to make it trustworthy, the most important thing is that we need to know that's what's happening. So if we don't give the reasons, if we cannot explain, so then obviously it will be very, very difficult to enable people to trust on that. So essentially, so we need to basically kind of convert the data driven into a model driven system, because obviously model driven could be controlled, model driven could be trusted. So we need to bring the data driven and model driven together. And as I explained before, the digital twins is to some extent a model, and we need to put data on the model to simply explain the process behind the model to see what are the steps happening, what are the decisions being taken. So, and the decisions that are being taken, we know that we could be quantified and we could build a mathematical relationship among the basically different entities. So fourth wave is not only speed, it's not only performance, but rather the explainability as well. And we need to basically make the models that are not probabilistic, rather on top of the data-driven probabilistic models, we could quantify what could be the possible outcomes from particular process. So with having said that, so we have been able to make some progress in this particular domain. For example, digital twins and contextual edge intelligence have been used to produce digital twins. Now, digital twins is essentially a complete copy of a physical entity, actually, and it could be a factory, it could be a production line, and then we enrich with different kind of data sources, and then we build different kind of finite element analysis or other kind of scenarios, actually. So in other words, that basically digital twin is a physical copy. Sorry, digital twins is a digital copy of a physical machine or asset or a factory. So now, interestingly, contextual intelligence, since digital twins make use of models and obviously data, so contextual edge intelligence is an important thing to basically enable digital twins to behave as real machines, because there is no single kind of component, there is no single kind of phenomena. There are hundreds of thousands of sensors. They're cooperating and basically building under a certain consistent model. So without contextual intelligence and cooperation, this is not possible. So for example, this is one example of a digital twins where an oil rig is being installed, and here obviously there are a lot of different angles. It could be weather, it could be wind, it could be water pressure, and it could be other kind of environmental factors that need to be understood in more or less real time. So one is a static model, and other is the changes happening dynamically, actually, that we need to bring these things together, actually. So that's one example of a digital twin. Another example of a digital twins is basically a plane, for example. It's a plane engine, actually. So so here, basically, for example, one is to just produce the digital twin of a plane engine. Another is to put it into practice. For example, impact of weather, for example, impact of, for example, temperature, for example, or wind, actually, performance, fuel consumption, quality of service, and other different aspects of quality assurance process, actually. So, so all this this happens if basically before we put something into productions, digital twins would enable us to look into all possible kind of conditions and possible kind of permutations or problems or issues that a physical version of the digital twins could face if that's put into production. So this is becoming, especially when the process is kind of time intensive or labor intensive or cost intensive or it's sensitive. So more and more digital twins are being produced, and that's a fantastic example of how edge intelligence is being put into practice, actually. So for example, these were our kind of initial results that we produced. So for example, we could create a digital twin of a piston now in almost 4 minutes. We could produce a digital twin of a cylinder in 30 minutes, for example. A whole jet compressor that was originally taking 3 months, now we could do it in under 42 hours, actually. And we are thinking to kind of bring this down to even under 24 hours, actually. And eventually where we are heading to, we want to make this process a kind of real time. So contextual intelligence would enable us to basically achieve real time performance, and we think that this should be achievable within next 2 years actually. So we should not only be able to produce the digital twins, rather it should also give us more or less real time performance. We should put these digital twins into operations to see basically that they are behaving as actual physical machines, and as the machine is evolving, our digital twins is also evolving as well. And it would not be just digital twin of the one component and one process. Rather, we were able to build our we were able to put together all those individual components into coherent machines and then put into practice, and we would be able to evolve those machines for future scenarios. For example, we would say that if this machine runs at a particular speed or a particular temperature under particular pressure, how it would behave. What would be the quality process? What would be the productivity, for example? So what are the failure modes, and what are the guarantees involved? So what insurance model, for example, could be sport, for example, if it's a car actually. So all these things would be able to be possible, and that's basically a contextual intelligence, or the edge intelligence would enable us to do that. So this is my last slide. So now we know that edge intelligence would be playing a big role. We know that we are evolving towards a distributed intelligence. We know that now number of devices work together to create a global model. But what about the model integrity? What about the model consistency? What happens if individual noisy data or an individual machine or individual node or individual edge device poison the training set, and the whole model basically is compromised? So we did some work actually, and we just published a paper that's in production actually. So what we did is that we for a particular set of FPGAs, we started looking into basically the signals, and we started looking into the signal, and we digitized the signals. And by digitizing the signals, we then started looking into energy patterns. So we know that particular algorithms work at a particular energy level actually. And based on those energy kind of indicators, we then started to map that how the data look like and what is the basically kind of patterns that this particular model is being trained. So we not only managed to infer the model from the energy traces, we reconstructed the whole model, and then we basically managed to penetrate to see that what happens if we basically kind of compromise the model. So obviously, as things become distributed, as things become global, this is going to become a more and more kind of a common process. So we need to obviously answer some fundamental questions if we have to make edge intelligence more prevalent. For example, we need to guarantee the authenticity of the data. We need to guarantee the security of the data transmission as well. And we also have to guarantee the fairness of the weight matrix, because let's suppose if we have 500 devices in a kind of a distributed model, so not few, basically 10 or 15 should overcome or should simply take the ownership of the whole learning process actually. So how can we make the whole learning process democratic? How can we allocate more or less even weights actually? So the security and integrity of a distributed AI model is very, very important. And through this basically we showed that, okay, accuracy of the model is important. Performance and latency of the model is important. And obviously, we know that speed is important as well. We know that it's resource efficient. But what happens if the model is basically compromised? So through that basically thing, we worked on a model integrity, because we know this would become more and more a kind of demanding, and people would be expecting us to think that, okay, model has been trained on few thousand different resources, but what if this model has been compromised? So what are the fundamental issues? So can machine learning or distributed AI could be used to validate integrity of the model as well? So this is only possible if we then use those edge devices that not only produce data, but to consume data at the same time as well, in a way that the whole consistency of the model is basically ensured. So this was my last slide. Thank you very much. And I would hand over to Professor Sarah Davies. Thank you very much.
Thank you, Ashiq, for handing over, and thank you for your very comprehensive and thought-provoking inaugural lecture. As part of our centenary, reflecting on how the university over its 100-year history has been working towards contributing to the better futures, or to improving the futures for our community and for wider society. And I think the inaugural lectures are a way of showcasing that contribution and impact of our current staff. And so in your lecture, you've certainly given us an insight into the way the fourth industrial revolution is transforming our lives, and also how artificial intelligence and machine learning are contributing to that. I think it was really interesting to understand those 4 waves that were coming through, and to understand where we are now in that process. It was great to see some of the applications for that in terms of health, in terms of Alzheimer's, but also in terms of understanding what we can do around predictive maintenance, and understanding how we can benefit commuters from spending more time on the trains and less time with their trains in the workshops. I think for me, the aspect around the digital twins, and just how you've demonstrated that you can really reduce the time to create those digital twins, to create those prototypes, and really enhance the development. And that's going to be essential across a range of industries in our future. So I would like to say thank you very much for your lecture. It's a great addition to the College and the Science and Engineering inaugural series, and I would like to thank everybody who's been online to listen to that, and to thank our speaker this evening. Thank you, Professor Anjum.